Hello. So we are studying strain measurement. So before starting, how do you measure a strain? Okay. How do you measure a strain? First of all, let us define what do you mean by a strain. So we already know strain is like, if you want to define strain, it is change in dimension to the original dimension. This is the basic definition of a strain. Now, the dimension change can be in two directions. Suppose this is my shaft, okay, and I am applying tensile force from both the side. Suppose I am applying tensile force T. So what will happen after some time, due to the application of tensile force, its length will increase. Suppose its length was L, so now the length will become L plus delta n, and its diameter will automatically decrease due to the application of tensile force. So its diameter will decrease by d minus delta t. So now when there is a change in dimension, now the dimension is changing from L to delta L plus delta L, which means that there is a change in dimension delta L. So change in dimension upon original dimension will be called as strain, and such kind of strain is called as longitudinal strain. Okay, and if there is a change in D, you can see there is a change in D. So if you subtract final dimension minus initial dimension, you will get another change which is called as delta B d by D. So such kind of dimension change upon original dimension will be called as lateral strain. Such kind of strains are called as lateral strain. It can also be written in terms of change in cross-sectional area upon original area, because whenever D changes, automatically A will also change. If A was initially A, then A might become as delta A. So whenever there is change in area upon original area, then it is called as lateral strain, or you can even say change in diameter upon original diameter. That is called as lateral strain. Okay, so I have defined for you what do you mean by lateral strain. Now what I'll try to do is, I'll just try to explain you what we are going to study and why are we going to study strain measurement, and what is the application of strain measurement, and what are the instruments that we can use for strain measurement. Now, strain measurements. Where do we use strain measurement? Actually, strain measurement device is also called a strain gauge. Some people call it as gauge, or some people call it as gauge, but it is better to pronounce it as gauge. And it is written, okay, so sorry. Its spelling is Gauge. Okay. So strain, whenever we are using some instrument which is used to measure the strain, automatically that instrument is called a strain gauge. Okay. There is one more name for strain gauge. I'll introduce that name later to you. Initially, what do I want you to know? That strain measurement devices are also called as strain gauges. Okay. Now, what are the different devices in which we use the principle of strain? Okay, so the first device that I would like to bring to your notice is, I can say, regarding strain. So I will like to introduce to you, I can say, like, for strain. Okay, so one of the devices is accelerometer. Okay, another device is load cell. I'm just giving you some examples. There is one more device which is torque cell. Okay, to list a few, I am just introducing to you some topics. It is also used in, I think, vibration measurement. Okay, I'm just testing some devices in which you use the principle of strain. Okay, all these devices that I've listed here, all these devices uses the principle of strain. Okay, now how do they use the principle of strain? I like to introduce to you. Now, it is used for load cell. Now, what do you mean by load cell? Load cell is also called as something which measures force. Okay, load cell measures forces. So when load cell measure forces, so you know that whenever there is force, okay, whenever there is force, due to force there will be some kind of a stress. Okay, due to the application of stress there will be some force. Okay, when you are applying some force there will be stress. Okay, and whenever there is stress there will be strain. So indirectly, whenever there is strain into the system, there will be some force acting on the system. Okay, so if you can correlate force and strain, okay, then it can be used for measurement of force also by using the application of strain. Like, strain is correlated to force. Okay, it is proportional to force. So automatically what we can say, that one of the device that is used to measure, that is implementing the principle of strain, is load cell. And what does the load cell measure? Load cell measures the force. Now I'll just take you to the next topic, like torque cell. Now, suppose there is a shaft. Suppose there is a shaft. Okay, I'm just drawing the cross sectional view. Suppose this is my shaft, and I know that this shaft will rotate. Okay, at some torque. Okay, and we know that torque is given by the force, radial force into the radial distance. Okay, so now we know that torque is nothing but force into r. Okay, and whenever there is some kind of a twist, whenever there is a turn, okay, there will be some kind of a twist. Suppose this is twisting at an angle theta. So now this strain, this will also induce some kind of a strain. This twisting, which we have studied in torsion, is also introducing some kind of strain. So ultimately, whenever there is torque, or whenever you can say there is couple or torque, automatically there will be strain induced, because torque is related to force, right? So automatically, this strain principle of strain induced into the system is also used to measure the torque. Okay, and such kinds of gauges are called as torque cells. So strain gauge is also used to measure the torque, and such kinds of gauges are called as torque cell. Now I would like to explain to you something more than this. It is also used for accelerometer, or you can even say vibrometer. Both means one and the same. Okay, it is used to measure acceleration, or you can even say it is used to measure the temperature. Okay, it is also used in temperature sensors. The principle of strain is actually incorporated in temperature sensor. Now I would like to explain how does it incorporate the strain principle, the temperature sensor, how does it incorporate the strain principle. I'll just introduce to you one formula that we have studied earlier also, that R is equal to R naught into 1 plus alpha t. And we also know, actually we also know that R is equal to rho L by A, right? We know all these formulas. Okay, so now we know that whenever there is some kind of dimensional change, this will change by amount delta L, and this will change by amount delta A. So automatically R will change, and whenever R will change, automatically R is related to T, so T will change. So ultimately, whenever there is resistance change, okay, suppose my strain, suppose this is my wire, okay, which is used as a strain gauge, and now I am applying some force on this wire. So when I apply some force on this wire, what will happen? The length and the cross-sectional area of this wire changes, and whenever the length and the cross-sectional wire area of the wire changes, automatically the resistance of the wire will change due to the presence of all these parameters. And whenever the resistance of the wire changes, since it is related to the temperature, so resistance will also lead to change in temperature. So it is actually used to measure the temperature. Okay, this is actually used, you'll see it in the coming topics in detail. Now, how does it incorporate acceleration measurement? We know that force is equal to mass into acceleration. So if there is force change and mass is constant, ultimately there will be some kind of change in acceleration. So if there is some kind of strain induced, okay, into the system, ultimately it will also lead to measurement of acceleration of the system. Okay, I hope you understood what are the basic applications and what are the types, what are the devices that incorporate strain principle. Okay, I've listed all the topics. It is used for vibration or acceleration. It is used for temperature sensor. It is for load cell, torque cell, and many more applications. Okay, now I would like to explain you some theory of strain gauge. Okay, I'll just explain you what do you mean by theory of strain gauge. So, theory of strain gauge. Theory of strain gauge is a very simple concept. It is not at all like you have not studied. I have just explained you that suppose this is my wire, okay, and what I'm saying, this wire is applied some load on both the sides. It can be tensile load and it can be compressive load. If I'm applying tensile load, automatically what will happen is the dimension of this wire will change, right? And the dimensions will change in both the direction. Lateral dimension, right? If I'm applying tensile force, lateral dimension will decrease, right? And longitudinal dimension, that is length, longitudinal dimension will increase, right? And that is one more thing. Since we know that rho is equal to R is equal to rho into L by A, this will change, this will change, and even the inherent resistivity. This is what, like R is proportional to L, and we know that R is inversely proportional to A. So what do we know? That R is proportional to L by A. When we try to remove the constant of proportionality, what do we get? It is equal to rho L by A. So this is nothing, this rho is actually but nothing a constant. Okay, this rho is a constant, right? So whenever there is a change in L, there is a change in A. The inherent constant of the instrument also changes, which is called as resistivity, or you can even say specific resistivity. Okay, the specific resistivity of the instrument also changes. Due to this reason, since the constant also varies due to the change in length and area, these instruments, the strain gauges, are also called as piezo-resistive gauges. I'm just giving you another name for the strain gauges. Okay, these are also called as piezo-resistive gauges. Okay, then so I've explained you the basic theory of strain gauge. What happens in strain gauge whenever there is change in rho, okay, whenever there is change in L, and whenever there is change in A, automatically this will lead to change in resistance, right? Now, whenever there is change in resistance, okay, what I'm saying, due to change in resistance, okay, since L and A are changing due to the strain induced, since we are applying some force, okay, so there is some stress induced, okay, and due to the stress induced there is change in the dimension, due to which there is strain induced. So these two factors actually these two, and also the constant varies, so these three factors are changing due to the contribution of strain, which is actually changing the resistance of the wire. Okay, which is actually changing the resistance of the wire. So what I'm trying to explain, that change in rho, change in L, and change in A will lead to strain. Okay, and it will also lead to change in resistance. Okay, this is the basic theory of a strain gauge. Now, if you want to learn strain gauges, there is one thing that you should actually know. Okay, that thing is called as gauge factor. Now, I would like to explain you what do you mean by a gauge factor. Gauge factor is represented by G to the suffix F. Now, a gauge factor is, you can say, it is a constant of the strain gauge. When you go to the market to buy a strain gauge, you have to specify that I need a strain gauge of this much gauge factor. Okay, so if you want to study the gauge factor, I'll just explain you what do you mean by gauge factor. I'll not give you the definition at the start. What I'll do is I'll just simplify the things for you. I'll start with R is equal to rho L by A. Okay, now what I'm saying, okay, lateral dimension changes. What I'm saying, lateral dimension changes. Okay, and I'm also saying longitudinal dimension will also change. Okay, longitudinal dimension also changes. Why do they change? Suppose I am applying a tensile force, you can even apply compressive force. Okay, there is not at all an issue in application of any of the force due to application of application of tensile force, or you can say tensile stress, right. Lateral dimension and longitudinal dimension changes due to the application of tensile force and tensile stress. And and we also know that resistivity of the material also changes, specific resistivity, and hence we can say specific resistivity of the material will also change, right? So when the specific resistivity of the material will change, automatically R will change, right? R will change, right? Okay, and when all these things are changing, like lateral dimension, longitudinal dimension, specific resistivity, we actually know R will change, and also strain will be induced. And when there is strain induced, there will be due to strain induced, due to induced strain, okay, there will be stress, right? There will be stress. So what I'll do is, since R is equal to rho L by 8, what I'll do is basically, see, all these factors are changing due to the application of strain, okay, due to the change in strain, and strain is happening due to the change in stress. So what I'll do, I'll just do one thing, I'll differentiate, okay, R with respect to resistance with respect to stress. Let the stress be called as S. Okay, so what I'm saying, I'll differentiate dr by ds. Okay, now since I'm differentiating dr by ds, now all these factors are changing due to strain, and we know that stress is proportional to strain, Book's law. Okay, so since stress is proportional to strain, so whenever all these factors are changing due to strain, actually stress is changing. Okay, so all these factors are dependent upon strain. So all these factors will be considered when there is a change in stress or strain. So I am considering stress. So this will be like, I can do one thing, rho by, what you can do is, uh, rho by A taken out constant, what will remain inside is dl by ds. Next, what you can do is I will do like uh, what I can do is I will take rho L constant. What will remain inside is d by ds of A, 1 by A, and whenever there is something like rho L constant to be taken out, what will remain is d. I'll just do one thing. I have to take L by A constant. So I'll take L by A constant. What will remain is d by ds of rho. Now what I'll do is I'll try to differentiate this thing in a proper sense. So I just have to differentiate this thing. Okay. I hope this is visible to you. So what I'm saying is dr by ds will be equal to rho a. Dl by ds we cannot simplify it further, so it will be as it is. Now rho L, we know that it is 1 upon a, right? It is 1 upon a. So 1 upon a ka derivative is like minus 1 upon a square into dA by ds, correct? I'll just shift myself to some other place. Okay, now what I'm saying is after doing this thing, again L by A is constant and d rho by ds cannot be simplified further, so it will be, one second, give me a second. Okay, this will be d rho by ds only, since we cannot simplify it further. Now what I'll do is I'll just do one thing. I will divide both sides by r. Now when I divide it by r, what will become is 1 by r dr by ds will be equal to rho by a into 1 by r dl by ds, right? And rho L, you can write it as minus rho L by a square, right? dA by ds, and 1 by r will also be there. And again there will be L by a into 1 by r d rho by ds. Now what I'll do is after writing this thing, I can do one thing for simplification is I can write the value of r. R is equal to rho L by a. I will put this value on RHS, in the RHS side only. I'll not do anything on the LHS. So 1 by r dr by ds will be as it is, will be equal to rho by a, and 1 upon r is rho L by a, and this will be dl by ds, right? Now this will be like rho L by a into a, you can see 1 upon r is there, right? So this will again be rho L by a, right, into dA by ds. Now this will again be L by a into r is there, rho L by a into d rho by ds. Now what I'll do is I'll just try to do, if I can do something. Rho eliminated, a eliminated. What will remain is 1 by L dl by ds. Now next thing, rho L by a, right? So 1 by a dA by ds, and rho L by a gets cancelled. What will remain is 1 by rho d rho by ds. Okay, so this is nothing but equal to 1 by r dr by ds. So I've got to some conclusion. Now I need to simplify this, but before simplifying, I'll just explain you something which is very important with regard to this equation. But this is very important, so I'll just explain it to you. Okay, what I want to explain you is, see, resistance is changing. Okay, I would like to add something like stress is there, stress is induced, right? Okay, when there is stress induced, what I am getting is there is change in resistance. Okay, there is change in resistance, and you can say rather than resistance you can write resistivity, right? And change in length and cross sectional area. Okay, this is the thing, this we already know, so I'm just trying to elaborate this thing for you. Now what I'll do is 1 by r dr by ds will be equal to, I think we got it as 1 by L dl by ds minus 1 by a dA by ds plus 1 by rho d rho by ds. Okay, Now what I'm going to do is, I'm just going to introduce a factor which is called as Poissons ratio. I'm not be correct in spelling because I'm writing it fast. So what do you mean by Poissons ratio? It is nothing but lateral strain upon longitudinal strain. This is the basic definition. Okay. Now, in our case, the force was tensile in nature. I hope you remember. If the force is tensile in nature, lateral strain will be like delta d by d, or you can even write delta a by a if you want to write. But since it is strain, so what do we have to write? This is delta d by d, and since it is singular dimension, and longitudinal stress, sorry, longitudinal strain change in length, it is there, so this will be delta L by L. Okay, now we know that if length is increasing, okay, suppose the length of this material, this thing is increasing, so its diameter will decrease. So this both ratios will be negative of each other. So we have to take, when we are considering mathematical equation, we have to consider its negativity also. Okay, so what I've written is Poisson's ratio is given by minus delta V by D upon delta L by A. Poisson's ratio is given by nu. Okay, so what I'm getting from here is delta d by d, okay, is equal to minus nu into delta L by L. Okay, now I will again do something very simple. I've taken a answer from your end. So I'll again write 1 upon r dr by ds will be equal to 1 upon L dl by ds. Now minus 1 upon a dA by ds plus 1 upon rho d rho by ds. Now what I'm saying to you is, just look at this term. Just look at this term. Okay. Now a, we know that a is equal to pi by 4 d square. Okay. Now I know that there is something like dA by ds. So what I'll do is, I'll take derivative of a with respect to stress. So pi by 4 is constant. This will be 2d. D square's derivative is 2d into dd by ds, right? So if I divide, see there is one a also. So what I'll do is I'll divide it by 1 by a. So 1 by a dA by ds will be something like pi d by 2, right? Into 1 by a is again pi by 4 d square into derivative of diameter with respect to stress. So what we can see is pi is getting cancelled. 2 is getting cancelled, 1d is getting cancelled, and this 2 will come to the numerator. So this will become like 2 by d dd by ds will be equal to 1 upon a dA by ds, right? So I'll just get to the thing. I'll just try to simplify. 1 upon r dr by ds will be equal to 1 upon L dl by ds, right? Minus 1 upon a dA by ds. We can see this value and this value are same, right? So what I'll do is I'll substitute it to be equal to 2 by d derivative of d with respect to s plus 1 upon rho d rho by ds. Okay. Now what I'm saying is, since we have done this, now we will use that Poisson's ratio. What was that Poisson's ratio like? Rho into delta L by L is equal to delta d by d. Now to have the delta L by L and delta d by d, what I'll do is I'll just look at this equation. This ds, there is an operator ds, so I'll multiply throughout by ds. If I multiply throughout by ds, what will remain is dr by r, right, will be equal to dl by l minus 2 times dd by d, okay, plus d rho by rho. This is the basic mathematical operation. We cannot do it in derivative, but if we are trying to consider delta s ds as s2 minus s1, okay, change in strain, so we can actually eliminate that term. So we have tried to eliminate that term by multiplying that operator, considering it to be very small. Okay, if it is very small, it can be considered to be s2 minus s1. So by considering it to be s2 minus s1, we have eliminated its derivative concept, and we have applied the infinitesimal concept of s2 minus s1. And if it is s2 minus s1, we can multiply it by s2 minus s1 throughout, like we can multiply it by ds and eliminate the term ds. Okay. Now what I'm saying is, after doing this thing, what I can do is dr by r is equal to dl by l minus 2 dd by d plus d rho by rho. Now I know rho into delta L by L is equal to minus dd by d. So automatically, if this is plus, this will become minus. So I can substitute this, you can see, as a value which is minus nu Poisson's ratio into delta L by L. So if I try to simplify dr by r, okay, before doing this is delta d, okay. So before using this term, what I'll do is I'll for an infinitesimal change, as I've told you earlier, for infinitesimal change or very small change or very small displacement, okay, there will be small change in length, there will be small change in displacement, the diameter will be small changed, the length will be changed small, okay, the resistivity will not vary that much, so the resistance will not vary that much. So what we can do is dr can be equated to be equal to d delta r, dl can be equated to be delta l, dd can be equated to be delta d, right? Similarly, d rho can be equated to be delta rho. So what I'm going to do after doing this thing, I'll just change the equation like delta r by r is equal to delta l by l minus delta, I think it was delta d by d. I think there was 2 also. If I can remember, I just don't remember it right now. I think there was some 2. Yeah, 2 times delta d by d, 2 times delta d by d plus delta rho by rho. Okay, now what I'm saying is after doing this thing, mu is into delta L by L minus will be equal to delta D by D. So I'll just substitute this value in this equation. So what will happen is delta rho by rho will be equal to delta L by L. This minus and this minus will become plus nu into delta L by L. Sorry, yeah, right. Plus delta rho by rho. Now what I'll do is I'll just give you something like delta L by L, delta L by L. So what I'll do is I will divide this equation, divide delta L by L on both the sides. I'm just trying to explain you gauge factor. I have not given you the definition because I wanted you to understand the concept. Okay. So if I'm dividing it by delta L by L, what will come here is delta R by R upon delta L by L will be equal to delta L by L upon delta L by L plus 2 times, again it is like delta L by L mu, 2 times mu delta L by L upon delta L by L plus delta rho by rho upon delta L by L. Now we know that this will get cancelled, so what will remain here is 1. This will be 2 mu because both terms will get cancelled again. Okay, and here it will be delta rho by rho upon delta L by L. Now I will define you what do you mean by gauge factor. I'll explain you now what do you mean by gauge factor. Okay, gauge factor, it is the relation between R and L, but what do you how do you define gauge factor? Gauge factor for a strain measuring instrument or a strain gauges, it is the ratio of per unit change in length, or you can check per unit change in resistance first, per unit change in resistance to per unit change in length. Okay, so it is the ratio of per unit change in resistance to per unit change in length. Now per unit change in resistance, so for writing this, gauge factor will be change in resistance, and if it is per unit we have to divide it by R, and change in length, if it is per unit we have to divide it by L. So this is the gauge factor. Now if you look at this term, what we have got, see, this was actually, this is what, this is the gauge factor, right? So this is my gauge factor, right? So I can write it for you in a simple way. Gauge factor is like 1 plus 2 nu plus delta rho by rho upon delta L by L. Now again, delta L by L, we know this is nothing but longitudinal strain. Okay, and the basic nomenclature that we use for longitudinal strain is epsilon. I'll just put here epsilon. Okay, so now if I want to write something for you, this is resistance change, because all these things are contributing. See, gauge factor was derived from one of the primary equation, which was R is equal to rho L by A. So there is something like there is a change in resistance. Okay, so what I'm saying, one will be like resistance change due to change in length, because you, if you remember the first term, the derivative, that the first term that we took was change in length. So resistance change due to change in length. Okay, now the second term, if you remember, that was related to cross sectional area, Okay, so the second term will be resistance change, because all are contributing to the resistance, because we started with the resistance. And gauge factor is per unit change in resistance to per unit change in length. So actually we are dealing with resistance. We may have written GF, but it is nothing but delta R by R upon delta L by L. I hope everyone is clear. The second term will be resistance change due to change in cross sectional area, right? And the third term is resistance change due to change in resistivity, change in resistivity. And due to this term, okay, due to the presence of this term, the strain gauges are also called as piezo-resistive gauge. I have also already told you, I think, when I started. Even if I have not told you, you can remember. Due to this resistance change due to change in resistivity, this is called a piezo. Piezo is like something which is inherent into the system. So inherent resistivity is changing due to the change in the main resistance. So resistance change due to the change in inherent resistivity of that wire, which will be acting as a strain gauge. And so we also call strain gauge as piezo-resistive gauge. So I've given you the definition. Now, suppose I'll just write it for you again. GF is equal to 1 plus 2 nu, right? And this is Poissons ratio, right? Plus delta rho by rho divided by, so sorry. This is actually very difficult. So sorry. Delta rho by rho upon epsilon. Okay. Now, what I would like to tell you is this, suppose resistivity is not actually changing that much. So sorry. Suppose the inherent resistivity of the material or the constant of the material is actually constant. So if resistivity, or you can say inherent resistivity, so sorry. So sorry. Inherent resistivity, I am saying, if it is constant, if this is constant, automatically delta rho will be equal to 0. So if delta rho, if the resistivity is considered to be constant, delta rho will be 0. So GF will be more like 1 plus 2 nu. So only there will be two contributions basically. One will be due to resistance change due to change in length, and its value is given by 1. And resistance change due to change in cross sectional area, its value is given by 2 nu. Okay, that's it. So we are done with strain gauge, strain measurement. And what do you mean by strain? What do you mean by strain measurement? What are the applications of strain measurement? And what do you mean by gauge factor? And what is the definition of gauge factor? It is per unit change in resistance to per unit change in length. And we started all of this thing just with a basic definition: R is equal to rho into L by A. Thank you so much.